Hello, welcome to the second session of Flight Vehicle Performance. I am Srinidhi Kukila. In this session, we are going to discuss about landing and balanced field length. So these are the contents of this session: landing, approach, transition, free roll, braking, and balanced field length. Landing. The landing flight phase consists of an approach starting at an altitude of 50 feet, a touchdown at a velocity of VTD, a free roll at constant velocity, and a braking deceleration until the aircraft comes to rest. The distance required to accomplish this is the landing distance SL. A schematic representation of the landing phase is shown in the figure. These are the four phases of landing: approach, transition, free roll, and braking. In the first portion of the landing phase, the aircraft starts at an elevation of 50 feet, as you can see in the image, that is h, and a velocity of V50 is equal to 1.3 into Vs. For military aircraft, the velocity V50 is 1.2 into Vs. The aircraft descends at a fixed angle gamma approach and velocity V50 until it reaches a transition height HTR. The horizontal distance for this portion of landing is designated as A. The second portion of the landing, the aircraft flies along a constant radius circular arc. At the bottom of the arc, the aircraft touches down at a velocity VTD, touchdown velocity, that's equal to 1.15 Vs. Just prior to the touchdown, the aircraft will flare to produce a positive angle of attack such that CL touchdown is equal to 0.8 CL max. Here, CL max is the maximum lift coefficient based on an enhanced flap configuration. The horizontal distance for this portion of landing is designated STR. In the third portion of the landing, the aircraft rolls freely at a constant velocity of VTD. The distance for this portion of landing is SFR. In the final part of the landing, the aircraft brakes to a stop. This distance is designated SB. The total landing distance is the sum of the distances in the four different phases. That is, SL is equal to distance during approach, distance during transition, distance during free roll, and distance during braking. For landing, a worst case scenario is assumed in which the weight of the aircraft at landing WL is given by WTO minus 0.5 W fuel. Here WTO is weight of the aircraft during takeoff. That is, it is assumed to be carrying 50% of its takeoff fuel weight. Next, we'll start off with the first phase of landing, approach. The approach is a constant velocity descent from the height of 50 feet to a height of HTR. The descent angle can be determined by the equation V50 into sine gamma is equal to V50 into T minus D by W. Most typically, the engines will be at idle. That is, when landing is happening, you will switch off the thrust, and the engines will be idle. That is, T is equal to 0. Then gamma approach, that is descent angle, is given by sine inverse of minus D by W. As a reference, a transport aircraft descent angle would be no larger than 3 degrees. The approach distance can be found from the equation SA is equal to HTR minus 50 divided by tan gamma approach, where HTR is the transition height is obtained from the transition portion from the next slide. That is the second phase of landing, transition. In the transition portion of landing, the aircraft flies along a circular arc with radius RTR. So this radius RTR is defined by the equation 1.23 into Vs whole square divided by 0.19 g, where g is the acceleration due to gravity. Vertical height during transition HTR can be found as RTR into 1 minus cos gamma approach. From these two equations, the horizontal ground distance in transition during landing is STR is equal to minus RTR into sine gamma approach. Next, the third phase of landing, free roll. During the free roll portion of the landing, the aircraft maintains constant velocity of VTD, touchdown velocity. As a convention, this is assumed to last for 3 seconds. The distance covered is SFR is equal to 3 into VTD, where VTD has units of feet per second to obtain SFR in feet. The last phase of landing, the final phase of landing, braking. The braking portion is governed by the same equation that were used to analyze the ground roll portion of takeoff. The deceleration in this case is given in the equation in free roll with the option that the engines will be at idle so that T is equal to 0, or the engines are equipped with thrust reversers. The drag includes all the quantities of same as in takeoff. For the rolling friction, the friction coefficients are larger because of braking. Here friction coefficient mu is, the values are for concrete it is 0.4 to 0.6, in hard turf it is 0.4, in firm and dry dirt it is 0.3, in soft turf it is almost zero point 0, in wet grass it is zero point 0.3, in snow or ice covered ground it is 0.07 to 0.1. Assuming that any reverse thrust is not a function of velocity, the braking distance is given by the first equation, that is equal to 1 by 2 into f of 2 ln f of 1 divided by f of 1 plus f of 2 f2 vtd square, where f1, the values of f1 and f2 are given, but here since this is braking, the aircraft will come to a rest, the engines will be switched off, so that is why thrust T is equal to 0. You have to apply T is equal to 0 for F1 and F2. So the total landing distance is the sum of distances in each portion. In addition, uh, for commercial aircraft, it is said to be 1.6 times longer than the calculated total distance in order to account for pilot differences. Next is the concept of balanced field length. The total takeoff distance is the sum of the different distances of the four faces. Then specifies the minimum airfield length that is required for the aircraft to take off. There is, however, another important airfield length at takeoff that is called balanced field length. This corresponds to the total field length which is required for safety in event that one engine of a multi-engine aircraft fails. So this is the schematic representation of balanced field length. Here at the bottom of the image you can see SBFL, that is the balanced field length. So in this event there is a reference velocity called decision speed. If the engine fails when the takeoff velocity is below the decision field, the field length needs to be sufficient to allow the aircraft to brake to a stop. If it fails above the decision speed, the field length has to be long enough to allow the aircraft to take off and clear the necessary obstacle height. The balanced field length can be estimated from the following fairly detailed empirical formula, that is the formula which is shown in the screen, that is SBFL, balanced field length distance, is equal to 0.863 by 1 plus 2.3 g into W by S divided by rho g, 0.8 CL max plus H obstacle into 1 by T AV by W minus U plus 2.7 plus 655 divided by square root of rho by rho SL, where for jet engine and propeller engine you have different values for TAV, and the capital G is gamma CL minus gamma minimum. So this is the concept of balanced field length. So in this session we have discussed about the second flight vehicle performance, landing. So under landing we have discussed about four different phases of landing, that is approach, transition, free roll and braking. Then the total distance traveled by the aircraft during landing, that is SL, is given by the summation of all these four phases. Next, we have discussed about the concept of balanced field length during takeoff. Thank you. If you have any suggestions, comments, doubts, please comment below. Thank you.